Afternoon today, and with Elizabeth Teresinha Gasparim, speaking about creating partition functions from singular varieties. Please.
You see. Wow, I'm very impressed to see so many people at this extremely difficult time to be here. It's too great afternoon. I have, by decision of my students, a method now that after the title, I must present the abstract so that it prevents me from giving a talk completely different from what I was supposed to do. So the story is this. I want to discuss partition functions, whichever partition functions, over singular varieties. And so this comes, the start of this is a long time ago, when I was the only mathematician at the Physics Institute in Calcutta. And they're extremely strong people, and every day they talk about partition function. And that was very frustrating because I didn't have a partition function. So I thought I'm going to do it. I will make one, right? So every day I would make a partition function. Then they would tell me, oh no, this one is the worst ever. It's much worse than the yesterday one. And so on and so on. About a month and a half of trying to make one partition function every day, I made one. And then the answer was, this one is even more ridiculous than the previous ones. And I said, okay, but is it a partition function? And then they were all quiet. Therefore, I knew I was right. It was a partition function. So it's about this partition function that I want to talk. The reason for the story is this. So you have the singular variety, and there are the two things the physicists do. By the way, I'm a mathematician, so you don't be too mean to me. I'm just a mathematician. But so there is resolution and there is smoothing. And so in either case, you choose something, and then you compute the thing about the resolution or the smoothing. But I don't want that. I want something for the singularity itself. So the idea is to sort out the problem. Right? Before I continue, next slide is the portrait of the organizers. It's recognizable, I can say, because I showed it to someone, and she recognized who is who, which is evident. The suggestion is, you see, because this is to thank the organizers, of course, for the great event, and then they should make a big poster of the voila. So I think it's completely obvious which one is which. In any case, that is my portrait of the organizers. All right, so now I'll try to get serious. So you see, but you already committed to making a poster and putting it on the wall, right? He agreed that before seeing it. So he agreed that before seeing it. Okay, so let's go to the singularity stuff. So there are two things about the singularity. So I'll discuss both cases, right? So in this case, for mathematicians, this is one of the favorite pictures, vanishing cycles, right? These appear on symplectic side. So physicist, actually Radefeva gave me this picture of the same thing, but physics picture. That's much more sensational, because if you think of collapsing star, let's say, then not only you see the singularity arriving, but you even see the monodrome around and everything. All right, so now there will be formulas. So I chose this partition function for the proposition that I will make. But it can be for any partition function. Like my former student, Thomas, who works at Google, he did the same method for, I don't know, the cross of BPS counting, Donaldson, Thomas, anything. It doesn't matter, whichever you like. You have the theory for smooth manifolds, and then you can do it for singular variety. So this one I choose because it's very simple to read. Because you start with actorical labial threefold, I'll have many of those. And then the partition function will have as data those capital Qs. The capital Qs are just the volumes of the P1s that will appear. So I'll show. These P1s that will appear, they come with signs, which will be plus or minus 1, according to their position inside the threefold. Too much competition. Right. So let's work with this partition function. That is topological strings, which is very simple. Right. Now, if I have the torical labial threefold, so by general property, first of all, it must be non-compact. And second, when you write the fan, so you put the arrows, it will be, so it has to be three-dimensional to be a threefold, and it will be Calabi-Yau precisely when all the vertices, all the arrows finish at a fixed plane. So then you draw a polygon, like here, which will triangulate. So then there are signs, right? Plus or minus 1, like in the Rodoguri-Sukowski and Yamazaki partition function. So when you subdivide, so the desingularization, so that would be a crampant resolution. The desingularization will be obtained whenever you take your polygon and triangulate it so that each triangle has area 1/2. So if you have the square, this will be a P1 embedded with normal bundle minus 1 minus 1. So this figure is the resolved conifold. Seems to be physicists' favorite conifold, Calabi-Yau threefold. And this is P1 embedded with minus 2 plus O, which is actually cotangent P1 cross E. That's a very, very simple. So I will argue today that this one is much more important. You will see why. I'll try to convince you. So now, let me give you some examples of the crampant resolutions that we use. So if I take this singularity, xy minus zw3. So you see this is 1, and this is 3. So those are the powers that appear there. So in this one, that's old work a long time ago. So my physics collaborator made this triangulation. And so we see, when you're done making all the possible triangulations, I can then compute the partition function for this, or for that, or for that, or for that. I can do it for all, right? If you have this one, it gets more exciting. Now you have more. And as you complicate the singularities, you have a lot more. See, my curiosity is, do you have more greens or do you have more red? Is there a preferred one? So if you're thinking like from point of view sort of cosmological, you find the singularity somewhere, can you tell where it came from? Is it more likely to have come from a thing that's very red or very green? It's unclear, right? So okay, so comes my recipe. That's the recipe I said that you can always apply. So you take those partition functions. Let's say I computed for all this guy. I have the triangulations. So take your Calabi-Yau threefold so that it has finitely many crampant resolutions. I only know that kind, so it's pretty much it always happens. So you can compute them all. And now you take the product. That's it. That's my partition function. Done. It's a step 1, but there's only step 1. Oh, it's only step 1. The second step is simply because I'm a mathematician, is that my theorems have hypotheses, and so therefore, you see. But that's all. That's how I propose. You do that, and then you see what happens. Okay, so let's see what happens, since we can compute. But of course, that means given your Calabi-Yau threefold, you must be able to find all the crampant resolutions, so you can calculate them all. Right? Now, before I continue, you should see, let me point out something. Sorry. In their statement, you see a toric Calabi-Yau threefold without compact force cycles. So if someone gives me the partition function that is made that actually considers the compact force cycles, then I can compute. But right now, we could compute only those types that are strips which have no compact force cycles. That means you can't create second-chain class, for example. But that means also that there is no internal points of the triangulation. I will have those later. Right, so what do we get? So this is an old thing. So you take any of those, right? Those are the strips, Ln. And then you take the product of all of them. So that's this side. That's when we already took all the product and we write, so you get a result. Then you can compare with this one. And it turns out one is just a power of the other. There's a prime. There's a small factor in front which gives the Euler characteristics. So that would be different. But otherwise, if you take all the crampant resolution, make all that product, then it turns out that you find another Calabi-Yau threefold that tells you what it is. No, this, the y will be, actually, now in the next one, y will be a surface. It's even worse than that. You see, what happens is that when you take that equation, you can take it in three-dimensional space, and that would be like times c. But it's even more than that. It can be also, so you can go down to 2 dimensions and have something like this. But now, you see, minus 2 lines all appear. So that means when you take all those, so Piotr used the vocabulary like this, that this surface, you can think of this as a surface, which has only minus 2 curves, knows about all the Krappan resolutions of the three folds we started with. So it somehow comes out of that. Okay, so this is old stuff, so I will move on. I want to give, before I move on, I want to give a few examples of where, so this, in 4 dimensions, we can have that. There won't be Calabi-Yau, only the 2 will be Calabi-Yau. So let's take that 2. And anyway, and these are the resolutions that I already mentioned. But I want to mention something about the 2-dimensional case before I continue. First of all, those are sets, right? In general, those 2-dimensional guys, they appear in mirror symmetry in a very particular way. So vector bundles on those are the objects dual to Lagrangians in cotangent projective space. It is what it is. For whatever reason it came about, I don't know, but that's how it is. So that's an appearance of those. And, geometry. This is my favorite geometry slides. It's, anyway. So now, for a moment, I will consider deformations. See, because I want both deformations and resolutions. Now, I see, like I saw also here, when people talk about deformation, that you consider a deformation, you allow the topological type to change. So we don't want to do that. And I will explain this. Balico gave us this example of why it is that we don't want to do that. So in Balico's example, is such that, I'll tell you what it does. It's long to read, but it's kind of simple to imagine. So you take P1 across a disk, any disk, as a family. So a trivial family, just P1s. And then you take 2 sections. Say one section is sort of varies and passes at infinity, and another section you make constant. So the 2 sections intersect in something. Now, you take this and remove the sections. Now see what you obtained. So where the 2 intersect, you have the P1, you took a point out, you have C, just complex plane. Everywhere else you have C minus a point. Of course, you can make C minus whatever many points you like. So if we allow the usual definition of algebraic geometry, flat family only, and put that for non-compact stuff, we get anything. You can just start taking points. So we don't want that. So because of Balico's example, for the deformations, we actually wrote down a definition. And in our definition, we simply require that it is the family, where the hell is it? That it is locally trivial in the C-infinity category. So smoothly, it's all the same. Only the holomorphic structure is going to change. This but not necessarily in the holomorphic category. That's done by the referee. We didn't have that. But anyway, so the topological type, the smooth type should remain. But you should write down the definition because I will be offering €100 for somebody who solves a problem that will appear right soon, but you have to use this definition. So there will be an award if you solve something quite simple. Right. So considering just these surfaces, we know everything about vector bundles, instantons, everything on those surfaces. And anyway, modular space of instantons or vector bundles, whichever you like best, I guess instantons, is some quasi-projective variety of dimension that depends on the charge of the instanton. We know exactly what it is. So it's a simple thing, assume we know it. Then we want to ask the question, if you now deform the variety a little bit, what happens? Okay, so what happens is this. So I take one of these, okay, I take any non-trivial deformation of it, and all the instantons have died. There isn't anything at all. It is quite catastrophic. Because of catastrophic result, this one, I will mention something about non-commutative deformations at the end, also because then I want to ask all of you, right? The whole everybody. I saw one physicist do a non-commutative, like quantization, let's say. And you take a thing, you make those things non-commute. Let's say ZU goes to partial Z and U. Done. How do you choose? There is like a ton, millions of different directions of quantization. How do you choose? I don't understand. So I will show you that. All right. So anyway, they had died. However, these deformations of Z2, so that is total space of cotangent bundle of P1. I will take one deformation of it, which has no instantons. However, at this particular deformation, I say is a vampire. So now I must explain how it is a vampire, but it's fun. So the particular, I'll try not to write. The particular deformation of the two I want to take is this adjoint orbit of SL2. So you take, I forgot how much I wrote. Sorry, no. Maybe I'll write for a moment. You take this element, you take this, and you take the adjoint orbit of this. That means all the conjugates of this guy. So this and this, you put a potential that takes it to C. So this will be then a Landau-Ginzburg model, which I call LG2. So that's the only Landau-Ginzburg model I will show today. And so because this is the orbit, so this will be Cartan-Killing pairing with a fixed matrix, which I couldn't choose any more trivially. I could choose the same. So it's the height function, the usual height function of Lie theory. So what it means, if you take an element of the orbit, you take a product and trace. So product of that by that trace. It's a very, very easy Landau-Ginzburg model. If somebody would like to see, I can explain later. But I want to show what it does. Not what it is, but what it does. This is the general explanation of what the function is. So for any orbit, I just wrote one, but for any orbit, you take a function that takes an element of the orbit and Cartan-Killing pairing with an edge that you fixed. And that thing has all the good conditions for the kind of Landau-Ginzburg model that is actually possible to compute the Fukaya category of. So we can compute. So you just have to believe us that I computed. However, this guy, this LG2, which I just wrote there, then what do? Then it's like this. So I was here in Trieste. We had been looking for 6 months or more for a projective variety X such that the derived category of coherent sheaves of X is equivalent to Fukaya category of that Landau-Ginzburg model we have there. So then I travel to Trento, I go to Balico, I give him the Fukaya category. It's very simple. It's two generators. It looks very much like height function on the sphere. It has two timbers, this and this, with some intersection that one can calculate. That's very simple. So I write it down and I say, Eduardo, give me a variety whose derived category of coherent sheaves is this. And he had a big laugh. He was so amused. He said, that is ridiculous. I said, oh, sensational. Now we have a theorem, so that doesn't exist. So what we mean by this, and that's really, really great fun, is for this exactly category, that simple Landau-Ginzburg model, you can take any projective variety, or quasi-projective, whatever, any algebraic variety, with or without singularities, it doesn't matter, and it is never going to give you a category equivalent to that one. So for that matter, I have a slide, which is representative of the situation at the time. All right. However, let's say B side is very smart too, right? Not just KG. So something is missing. So what can we do? All right. So I did a different thing, but you see, it again comes from the same thing. So if I take that famous cotangent P1, contract the zero section, you get some singularity. This guy has on it a sheaf that's not perfect. Now, perfect means it's not as written as a sequence of finitely many vector bundles. Right? This is the thing. But searching for a non-perfect sheaf is like searching for an irrational number, right? You know there's got to be many. But in reality, there are like 3 irrational numbers only. We all know, right? It's e, it's pi, and it's the root of 2. That's it. Those are the only ones. So it's terribly difficult. But I knew this guy because of the instantons on those surfaces. So that's not perfect. So that generates something over that kind of singularity. Therefore, I then have a result. So homological mirror symmetry has now there's a different way to state. The first way is you look for the derived category of coherent sheaves of some algebraic variety. Fails. You write different thing, different algebraic variety altogether with a potential in it, and you compute the Orlov category of singularities. That means you collect all the possible perfect, non-perfect sheaves. That means that all the ones that were here are 0, right? Because you quotient by the ones that are perfect. So those generators of the coherent sheaf in general will die pretty much. And if it's a smooth variety, it will really be 0. So that this other thing does give. Anyway, so you see, even you take the deformation, that thing has no physics in it, apparently. And then it also has no mirrors in one way, it's like all kinds of stuff. Right, so that was one statement of why that -2 curve is good. Now, continue. It says, so that's second half. End of a football pause, we go back. That was the only hard algebraic geometry part that I was going to show, so don't hate me yet. Now, so what? I said those things are kind of old, right? So in physics conference, you talk of things that are new. Like in mathematics conference, you can present some work you did 35 years ago or something. But in physics, you should do something new. So what's new? The new thing is this. So I started working with Carlos Simpson. He does proof-assisted stuff in generally machine learning, AI calculations. And it turns out that the steps, the learning steps for the algorithm that you need to verify proofs, which are at each step, is this true, is it false, or we don't know, are the exact same steps as you want to do the triangulation from this vertex to that. Do I put a vertex? Do I not put a vertex? Or I don't know if I put a vertex. So the algorithm has exactly the same. So this week, on Monday, he gave this talk about the things that, well, without the football, I'm pretty sure. But he explained sort of the same triangulation stuff. But now, you see, for him, or for the computer, you can have internal points. So I did one. So Carlos did, so this is where we are right now with the AI part. So he took, about a month ago, he took, I'll put the figure, it's easier. He took this with 1, 2, 3, 4 internal points. And then you give it to the computer inside, calculate all the possible triangulations. All right, so it can do. Now, I want you to guess how many steps the computer took to find all the triangulations of this. 10, 20, 150, any guess? I know, because you see, you can think, can you do better than the computer? Even I can do better than the computer on that one, I think. But the problem is not to calculate many, is that how do you know if you have finished? That's really hard, right? In any case, no guess. You know, I put this for a group of high school students that they asked for some mathematics about 2 weeks ago, and just one girl guessed the exact number at the first try. So the number of steps is 25,000. That's what the computer took. So that's not good, that's too much. But anyway, these large models, they don't really care. But then Carlos spent a bit over a month playing with it, and then he went down to, for that figure, to 3,800 steps. And he couldn't go down for it any further. But he is, of course, a very smart guy, we know that. So he calculated theoretically what is the minimum possible amount of steps. And you need something like 3,784. So we're doing pretty good. Anyway, so that's the news, is that now you can take a Calabian. Oh, No, don't die. Because when it did that earlier, it disappeared forever. Ah, good. So now we can calculate for such kinds of things which have internal points. So the compact for cycles are there, which I wanted. So I took the drawings. You see the C, it was written C24, the one that had 12 triangulations. And I extended it with this triangle. So see, this was the thing I have, which we knew all the triangulations of them. I extended like this, therefore you must triangulate here. I'm forced to put this one. And now I want to show the other ones which don't come from that. So they don't have this thing. That means what the extra triangulations that don't come from just taking the old ones and putting this little bit on top. So then I got those. I'm pretty sure it's all, but we don't know. So these are the new ones. Okay, right. Green, blue, etc. stuff. Then we can do the same, right? We can product and so on. Well, we could, but we can't because I drew blue lines. Now I have asked many physicists. You guys, please feel free to give me an explanation which is different from that. But I am told that this two-dimensional figure, where red represents fermions and green represents bosons and the blue represents anions. And I'm supposed to say that. Only Tsiolkovsky is very happy about it because it immediately gives braiding and whatever other knot stuff. But anyway, anybody who has a different interpretation, please offer it. Because that's where we are. So now if we know how to compute those, so let's take the same type, no? Because I only have shown one partition function. This morning I was looking for another partition function, but I wanted an ugly one, but nobody would give me an ugly one. And besides, Julius told me there doesn't exist. All partition functions are born beautiful, according to him. So, and I wanted a worse one. But since we only have that one, we go to that. So this reasonably new paper, a couple of years ago, this Chen and Tsiolkovsky, they take these figures, do some geometric transition, add a brain, and calculate partition function for a refined topological partition function. So we can do that because if I have this, there is a recipe. You do the dual graph. So dual graph. So Bruno drew it. It's kind of ugly, but what do? Right. You're supposed to have perpendicular lines to everything. You go and draw perpendicular stuff. So it looks ugly, but okay. So this is a dual graph. So it's the kind of figure they have. So when you have that, let me go back. You have that. You're going to choose some things to kill. They make circles. And you disappear with them, you see. They kill the compact for cycle, which I find terribly tragically, but in any case, it's done. So in theory, at least we could compute that. But we can't. Because that was the first triangulation. This is the last one. And let's draw the dual graph of this one. And it turns out it's not possible. You cannot do it. So it is a try, but you see this one is not there. So you have two steps to do. Step one, each triangle should have an interior point that you should put, and then, so these are the vertices of the dual graph. And then you're supposed to take vertices of the triangulation. It's difficult to see here. So like this one and this one. These ones should be perpendicular to the original vertices. And it's not possible. There is simply no way to do it. So we can't compute that. Something else has to be done. Piotr's proposition yesterday was that we simply must allow the dual graph to have vertices outside the figure. So that's where we are right now, but we'll see. But still, I'm not happy because we're going to kill the fourth cycle, which I don't want to kill. But in any case, it's going on. Of course, now, once we have solved this, then we can triangulate with Carlos' AI algorithm and so on, and we're in business, and then we'll product, and we'll see what happens. So right now, we don't know. Like in the case of the strips, the only conclusion we could have was that if you find the singularity and you knew that it has to be resolved by -1 and -2 lines, that you must assume it was all -2. That was the conclusion, right? But in these cases, we don't know. Besides, we have to do knots. So these are examples of toric stuff. Let me comment on. Okay, this is the part we can do. So this compact for cycles. we'll bring second Chern class, which I want. I like that, right? And so suppose I take a surface, a complex surface Y, any complex surface. Our business recently has been to make surfaces with prescribed number of singular fibers, with hyperelliptic fibers or whatever, but it doesn't matter. You take your complex surface Y, any of it. You want to put it as a 4-cycle inside the Calabi-Yau threefold. And the business non-compact stuff, if it's toric, it's compulsory. There is only one way to do it. It has to be inside of the total space of the canonical bundle. So that's what you do. So you take total space of canonical bundle of Y, and that's your Calabi-Yau threefold. Fine. But then it's very easy because it's just one application of a junction formula. So in one step, right? Balico does it in the sleep. Does it. So you took Y, then the second Chern class of the threefold X is this, whatever it is. So what Chern classes can we get? So general result 1. If you want a rational one, so if you want a toric one, something's missing. Right, you didn't read correctly. Right, so if you want a toric one, every even integer bigger or equal to -6, you can construct a Calabi-Yau threefold with that number as second Chern class. And if you don't mind that if it's not toric, then for any even integer, you can construct a Calabi-Yau threefold that has a 4-cycle that has that number as a second Chern class. And it has to be even. It can only be even because there is this standard equality. So you add C1 squared to the two sides, and you see that the second Chern class must be even. So you can get all of them and then calculate stuff. So that means we know many. We don't know what to compute. Not in this partition function or in any one of those. Okay, so that was a small pause. And that's the end of commutative part. Non-commutative part I show very short. Something very. I always talk less than the time. Because poor audience, you have to listen. So, but now is only non-commutative part, where I want to show you just something. You deform the variety non-commutatively, so quantization and so on. And I want you to tell me, do you have a preference between two things, which I will show at the end. I forgot what comes next, something. Right. So I had said that if we took those surfaces and you deform commutatively, then all the instantons had died. So that is actually the reason why we did non-commutative stuff first. Because the instantons couldn't disappear completely to all directions. They have to go somewhere if you deform. So they went all to the non-commutative directions. There is a fancy statement about constructible sheaf, etc. But the issue is there are many instantons going to the non-commutative directions. So I do the same for the threefolds now to count BPS states. I forgot about that. So I'm going to show only W2. That's the second. I promise that the -20 thing I was going to try to convince you is the most important of the Calabi-Yau threefolds, right? So this is copied directly from Yang Hui-He's book about how many Calabi-Yau threefolds are there. And this he gave to us in 2020, during the pandemic, in online seminar. It was kind of this stage of how many they had. So, Bruno, my former student, entered the book by doing the following thing. Here's Bruno celebrating. You take that triangle guy, right? And so that is we call it W2. That is cotangent of P1 plus O, or cotangent P1 cross C. That particular Calabi-Yau threefold has infinitely many distinct commutative deformations, different algebraic varieties. Here is the thing that I pay €100 for whoever. I would be so happy to pay that and that someone does it. So the one that we call W1, that's a resolved conifold, right? That's O minus 1 plus O minus 1 on P1. That's the standard resolved conifold the physicists know very well. The question is, does it have a non-trivial deformation, but that keeps fixed the topology, keeps fixed the C-infinity type? Not the singularity itself, the resolved one, right? The square root, it's a non-non. So it may have nothing, but I don't believe it. Okay, oh, that's Baliku's example again. And okay, so that's the result I said. Not only that, so there is W1, W2, W3. You can do whatever vector bundle you do the other one minus 2, you get Calabi-Yau threefold as total space. All of them have infinitely many isomorphism types of commutative deformations. But the W1 doesn't seem to have anything, which I don't think is possible. In any case, let's go with 2. So I want to just comment. Again, it looks like fancy results, but we don't need the details of the fancy results. I need just a statement what I want to say. Do this. To do the non-commutative deformation, what we do? You have to choose a Poisson structure, which will give you the first number in front of the H bar, and then extend it to a star product, right? So we take standard moduli spaces of vector bundles over those Calabi-Yau threefolds, which we need to compute anything. I don't know, BPS counting, or whatever partition, Donaldson-Thomas, stuff that needs Calabi-Yau threefolds. And we know what they are. When you take the deformations in general, the moduli spaces can go at whatever less dimension. So you have some fixed dimension for the initial threefold. You have all the different directions. There will be a direction where the dimension of moduli decreases by 1. There will be directions where it decreases by 2, etc., until directions when it dies. So all kinds of things happen in different directions. So we know that, right? It's similar for the non-commutative ones. Oh. Right, so similar thing happens when you choose a Poisson deformation. So now you have the variety, you put a Poisson deformation. It's written algebraically. I say algebraic collaborators, but it's not me. But so, for example, things have to be written because we're in a threefold as sections of lambda 3 of the cotangent bond, No, what tangent? I forgot. But anyway, no, lambda 3 of tangent. Anyway, it turns out a three-dimensional rank 3 vector bundle, so it's written like this, but like this Poisson structure will be in coordinates. It's Z, U1, U2. So this will be the Z wedge the U2. And this will be the U1, the U2. So it's the one that's missing. So you write all the possible Poisson structures. This is a very big space generated by 5 different Poisson structures. It has some relations, etc. But anyway, it's very easy. You just find by vector fields that satisfy integrability condition. So the Farad generators, which are not isomorphic, because 1 and 5 are isomorphic, but just they have these things are degeneracy cycles. That means the points which are leaves. So the leaves will be two-dimensional in general, and then there will be the points which are form a leaves, so the degenerate leaf. So the parts where when you do the symplectic foliation for the Poisson structure, so you have all these two-dimensional leaves, except for some which are degenerate. There is one that's holomorphic symplectic, so there's one that has no degeneracy at all. And there are others which have, so the pictures are here, not for any detail, but to show how different they are. You see, this one has a plane of degeneracies, this one has a P1 cross C of degeneracies, this one has disconnected and degeneracy set, right? One line and one plane, and the one has nothing. So they are very different. We can then, of course, do non-commutative deformation in any direction. So you choose a Poisson structure corresponding to any of those. Oh, these are the leaves. I don't want to do that. You choose your Poisson structure, and then you put it as a first element, right? The coefficient of H bar, and complete it to some star product. Fine. So we did that. So suppose we have this now for a fixed choice of sigma. So language, right? So you have to put not structure sheaf, but structure sheaf with many H bars. That's fine. But anyway, so now we can define moduli. So now a new commutative deformation will have vector bundles on it and modular vector bundles on it. The surprising thing is just how easy it is to do moduli spaces of vector bundles over the non-commutative deformation. It is extremely easy because the isomorphism is this. So in general, you want to do modular vector bundles. Isomorphism is you change coordinates on both sides. For the modular vector bundles on the non-commutative quantization, or whichever you want to call it, but on the non-commutative thing, you do the same thing, but you star product instead of product. And then you calculate. So that's the isomorphism. That means we can calculate the modular vector bundles and what's the effect of the non-commutative deformation on them. All right, so, sorry. Yeah, this is notation of the modular space. So it depends on the choice of Poisson structure that's here. And now, okay, two things more only. First thing, if you choose your Poisson structure the nicest possible, like as simplest, that means like, for example, when you do the first order deformation, it is highly non-vanishing. It's good, like all the coefficients are non-zero and sort of as independent as possible on the very first order deformation. Then the modular of bundles on the non-commutative deformation is isomorphic to the original one. So in that direction, nothing happens. So I don't know if that's good or bad, but that's how it is. On the other side, there are many different possibilities. So there's ones that we gave a name, we called extremo, when it starts actually having new things at second order. So H bar squared and so on and higher, but not less. And then this is what happens. Now, the new modular space that you obtain for one of those Poisson structures is enormously bigger. So you see, if I take, this is my local charge. Like this is my charge of the vector bundle over the initial guy. So, so now we have that the new modular space looks like a sheaf over the classical one, where the ranks of the regular stocks are to j minus 2, so you can be as big as you like, but with many singular things up to all the way to 4j. So let's say your charge was okay, let's say 2, right? So then you have that the new guy has 2 dimensions more for the fibers, but in some fibers it has, 15. So it gets enormously bigger. So that is the question. So this is the last part. So what non-commutative deformation or what quantization we should choose? What do you like better as a physicist? The one that maintains the modular space, the ones that kill the modular space, or the ones that make it enormously higher, much huger? How do I know? How do I know which one to choose? So what I would like someone to produce is the following, which may be very hard, but that I would be very happy. You give me some functional that I need to minimize, taking values on those. But how does one choose? I mean, you gotta have some favorite. I saw people having favorite ones, saying, oh, but if I'm on the A side, I choose this, on B side, I choose that. How do we choose? So we don't know. So that's homework. Besides the one that is $100 more. Then there's some people that don't know me, I am very proud I learned to make this. That's my biggest accomplishment in the recent, you can try, it works. Okay, so that was what I wanted to say. Thank you so much for paying attention. Yes?
You showed a picture of some triangulation of this polygon for which you said the partition cannot be computed, right?
The dual graph cannot be computed. Well, you can't get a dual graph with the rules that you see the vertices are one inside each of the triangles, and the edges are perpendicular to the edges of the triangulation. With those conditions, it doesn't exist. It's worse than cannot be computed. It's impossible. Yes, that bad. So then one has to choose which way to fix it, right? But with the usual recipe, which worked fine for the case of Calabi-Yau without 4 cycles, you can't solve it.
You said that the correct procedure to multiply a partition function that corresponds to different triangulations.
I didn't say it's a correct procedure. I said that's what we did. I have had both things. People say that's horrible and people that say it's great. So both things can happen. Who knows? I must say that at least I have had once very, very, very sensational person who told me that's very good. The person who told me it's very good is Roger Payne Rhodes. so that's a good vote, let's say. But many people have told me it's terrible. In particular, someone from CISA, some time ago, I gave a talk in Scotland. They told me this is very bad. I don't like it. Well, fine, you cannot like it. That was okay, right? I make a partition function. You don't need to like it. It's okay, right? Then don't use it. So partition functions are made. So this is the ugly one. He doesn't like it. So you see, I must conclude the ugly partition function I was looking for is mine. But anyway, there you go. Yes.
These different triangulations are related by close conditions.
Right.
And they
correct.
This partition function should be kind of very similar before and after the close condition. So something like just the power of some main object, maybe with some
power of this, yes. So, but in the strips case, we calculated power of who? It's a power of one particular configuration, which that's what we were looking for, right, from the initial question. So, is power of a singularity, not the same singularity, another one, more degenerate singularity, which has an entire line of singularities. So you see, the ones I was giving have a point singularity only. After the product, it gives the same as a power of something which has an entire line of singularities. So you have to assume that the original singularity is a very long configuration, exactly like the catastrophe. How is it called? Gravitational collapse thing. The physics picture that I put, exactly like that, an entire line of singularities. That's the configuration that carries the most probability of having been there. Good or bad, I don't know. That's what happened. So yes. Yes.
This was nice talk.
Oh, thank you.
I have a question on this partition function. So I guess you could play the same game also.
To any partition function, yes. Please do, please do.
Yes. Take like a non-toric singularity.
Yes, of course. Of course. You just take the Krapin resolutions. But you must know. So yeah, so Thomas Krapin, my former student, he did that. He turned out very beautiful things with Donaldson-Thomas stuff. Because he knows all the moduli of bundles and sheaves on the sum threefold.
Yeah, so like this kind of new partition function basically encodes all the GB variants in the different chambers.
Yes. Yes, you can object and say it's not valid anyway. Well, it's valid maybe in a little space, but
chamber by chamber.
Yes. Yeah. Or you can take just a few, right? And you say, look, I want this region, and you choose that. You can do and see what you have.
It's like encoding the whole KRCOM kind of like.
So, right.
In one partition function.
The check that we did very carefully is for the Krasov partition function because we know that one very well and it all works very nicely. Yeah.
Okay.
But that one I understand, so that's not fun. I want the new ones that I can. Right.
Any other questions? I have one.
Yes, please.
So when you have the triangulations, you have many triangulations, imagine.
There will be many.
Do you have any way of knowing which of them have an allowed dual graph or not? Is there?
But the strips they always have, but I don't know. I took one because I wanted to prepare one new thing here, and the first one I chose already says stuff that's not allowed. So
but there's no a priori way of knowing.
I had no idea that was going to happen. I did all the triangulations. I happily sent it to Bruno and to Sukolsky, and both of them was like, no, you can't do it, impossible. Okay, fine, great, even better. But then I'm wrong, but I'm always wrong, so it's the surprise. It is fine by me, so long as they work, right? I have no idea. Maybe it will always happen. But this onion story, it is really bothering me. I don't want to have blue lines. But it seems unavoidable. I don't know. Many new things, I guess, are going to appear. But of course, we can machine calculate and see if the computer finds. Otherwise, we just allow now that the idea now is to allow that some points of the dual graph, vertices will be outside. I'm outvoted 3 against 1. I find it horrible, but fine if it's horrible. I like ugly things too, so no problem. We'll see. Who did the homework? I want somebody to get the 100. What?
€100?
Yeah, I'm happy to pay the €100, but for someone.
Fine, they can do the homework during the coffee.
Right. Coffee is necessary. It is a terribly difficult time to stay awake after sunny and lunchtime.
Let's thank Elizabeth again.
Thank you.